You're watching a cosmic detective story unfold in real time. March 27th, 2024. Catalina Sky Survey picks up a dot moving against the stars. They call it 3I/Atlas. For months, astronomers think they're tracking just another asteroid. Then something changes. The dot grows a tail. The orbit screams comet. But this isn't your textbook, dirty snowball. Every 16 hours, 3I/Atlas spins like a broken top. Its tail appears and vanishes like smoke. The brightness swings wild. What you're seeing breaks the rules. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA JPL and the International Astronomical Union. Now back to the story. 3. I/Atlas sits in a category that shouldn't exist. Asteroids don't grow tails. Comets don't spin this fast without tearing apart. But here's your smoking gun, a rock that learned to breathe fire 28 million miles from the sun. The asteroid terrestrial impact. Last alert system caught the first images. Atlas telescopes in Hawaii and South Africa tracked the motion. By April, the European Space Agency confirmed what nobody wanted to say out loud. This thing defies classification. The 16-hour rotation period tells the first part of the story. Most asteroids tumble lazy, rotation periods measured in days or weeks. 3I/Atlas completes a full spin in 2/3 of an Earth day. That's fast enough to generate serious centrifugal stress. Picture a football spinning so hard the leather starts to peel. At 3I/Atlas's size, roughly 1 kilometer across, this rotation rate pushes the structural limits. Any faster and the whole thing would fly apart. But speed isn't the mystery. The mystery is what happens during those 16 hours. Ground-based telescopes track the brightness curve. Every 8 hours, 3I/Atlas dims by half a magnitude. Then it brightens again. The pattern repeats like clockwork. This isn't random tumbling. This is a controlled rotation around a specific axis. Something keeps this object locked in a precise spin. The tail changes everything. August 20th, dark 2024. Multiple observatories confirmed dust and gas streaming from 3I/Atlas. The tail stretches 40,000 kilometers, longer than 3 Earth diameters. But here's the kicker. The tail doesn't point directly away from the sun like every comet in the textbooks. It curves, it bends, it follows the rotation of the parent body. Spectral analysis reveals the tail's composition. Silicon dioxide, magnesium silicate, iron particles. This isn't water ice sublimating like a normal comet. This is rock dust. Mineral grains being torn from the surface and flung into space. 3I/Atlas isn't melting, it's disintegrating. The European Southern Observatory's Very Large Telescope captures the sequence in detail. During the brightest phase of rotation, the tail grows thick and prominent. During the dim phase, it fades to nearly invisible. The dust production follows the light curve exactly. Whatever surface feature creates the brightness variation also drives the mass loss. Planetary scientists call this a disrupted asteroid. The rotation tears material loose from specific regions, weak spots in the structure, fracture zones where the rock can't hold against centrifugal force. Every 16 hours, these zones face the sun and heat up. Thermal expansion cracks the surface. Dust particles break free and stream away. But thermal effects alone can't explain the timing. The sun's heat should create steady outgassing, not pulsed events tied to rotation. Something else drives the process. The leading theory points to the object's shape. 3I/Atlas isn't round. Radar observations suggest a highly elongated profile. Think of a spinning baton rather than a spinning ball. The baton shape explains the brightness curve. When the long axis points toward Earth, you see maximum surface area, maximum brightness. When the short axis points toward you, the object appears dimmer. The 8-hour cycle matches exactly what you'd expect from an elongated body rotating every 16 hours. Now add the tail mechanics. The elongated shape creates uneven heating. The narrow ends heat up faster than the thick middle. Thermal stress concentrates at the tips. Rock expands and contracts in cycles. Microfractures open and close. During each rotation, the stressed material reaches a breaking point. Dust jets erupt from the heated ends. Hubble Space Telescope images confirm this model. The tail originates from 2 distinct points on the object's surface, not a diffuse cloud like normal comet outgassing. 2 focused jets firing in opposite directions. The jets align with the rotation axis. As 3I/Atlas spins, the jets sweep through space like lighthouse beams. The mass loss rate tells you how long this can continue. Spectroscopic measurements put the dust production at roughly 10 kilograms per second. That sounds small until you calculate the cumulative effect. In 1 Earth year, 3I/Atlas loses 300 tons of material. The object amasses somewhere around 10 billion tons. At current rates, it could continue shedding dust for 30,000 years, but the process isn't linear. Disrupted asteroids follow a cascade pattern. Initial mass loss weakens the structure. Weaker structure allows faster rotation. Faster rotation increases stress. Increased stress accelerates mass loss. The feedback loop drives the object toward total fragmentation. 3. I-Atlas sits somewhere in the middle of this cascade, still coherent enough to maintain its shape, still spinning fast enough to tear itself apart. The 16-hour period puts it right at the edge of stability. Any faster and a catastrophic breakup becomes inevitable. The discovery timing matters. March 2024 marks the first detection. But 3I Atlas didn't suddenly start disintegrating. The disruption process began years or decades earlier. Astronomers simply hadn't looked in the right place at the right time. How many similar objects orbit undetected? Minor Planet Center data suggest 3. I-Atlas belongs to a larger population. Active asteroids, objects that show comet-like behavior without comet-like composition. The catalog lists fewer than 30 confirmed cases. But selection bias skews the numbers low. These objects are hard to find and harder to study. Most disrupted asteroids fade quickly. The dust production creates a temporary brightening. Then the object dims below detection limits. 3. I-Atlas caught attention during its peak activity phase. In 5 years, it might be invisible to ground-based telescopes. The orbital dynamics add another layer to the story. 3. I-Atlas follows a highly elliptical path around the Sun. Perihelion distance, closest approach, sits at 1.6 astronomical units. Aphelion distance, farthest point, reaches 4.6 AU. The orbit takes 5.5 years to complete. This trajectory explains the disruption timeline. Near perihelion, solar heating intensifies. Thermal stress increases. Dust production peaks. Near aphelion, the object cools and stabilizes. The disruption cycle follows the orbital cycle. 3. I-Atlas becomes most active during its closest approach to the Sun. Ground-based observations track this pattern. Brightness measurements from March through November 2024 show steady decline. As 3. I-Atlas moves away from perihelion, both the tail and the rotation-linked brightness variations weaken. The object is entering a dormant phase, but dormant doesn't mean dead. Computer models predict renewed activity around 2027. When 3 I-Atlas returns to perihelion, the thermal stress will rebuild, the dust jets will reactivate, the tail will regrow. Each orbital cycle brings another round of disruption. The long-term fate depends on structural details nobody can measure directly. If 3 I-Atlas consists of loosely bound rubble, a rubble pile held together by gravity, it will eventually shake itself apart completely. If it's a solid chunk of rock with localized weak zones, it might survive dozens of orbital cycles. Spectral analysis offers clues about internal structure. The mineral composition matches ordinary chondrite meteorites, silicate rock with metal inclusions. This material can withstand significant stress, but not indefinitely. Repeated thermal cycling creates fatigue fractures. Over thousands of years, even solid rock develops fatal weaknesses. The discovery of 3 I-Atlas changes how astronomers think about the asteroid belt. These objects aren't just ancient debris left over from planetary formation. They're dynamic, evolving systems. Some grow tails, some change orbits, some break apart in real time. Near-Earth asteroid surveys now watch for similar behavior. The Catalina Sky Survey, Linear, and NEOWISE missions scan for objects showing unexpected brightness changes. The goal isn't just planetary defense, tracking rocks that might hit Earth. It's understanding how the solar system continues to evolve. 3. I-Atlas represents a transition state. Not quite asteroid, not quite comet, something in between that astronomers are still learning to recognize. The 16-hour spin rate and pulsed dust jets mark it as a member of a previously unknown population. But here's what really matters. 3. I-Atlas didn't just appear in March 2024. It's been orbiting the Sun for millions of years, spinning and heating and slowly tearing itself apart. The disruption you're watching began long before humans existed. What you see now is the final act of a process that started when mammoths walked the Earth. The Gaia Space Observatory has been measuring asteroid positions and brightnesses since 2014. Archival data shows 3 I-Atlas experienced similar disruption events in 2017 and 2020. Each event lasted several months before the object returned to dormancy. The current disruption isn't unique, it's part of a repeating cycle. Deep sky surveys going back decades might contain earlier records of 3 I-Atlas activity. Digital archives from Mount Palomar and other observatories hold millions of images. Artificial intelligence systems now search these archives for objects showing comet-like behavior. 3I Atlas might appear in photographs from the 1990s or earlier. The search for similar objects continues across multiple wavelengths. Infrared telescopes detect thermal emission from dust clouds. Visible light surveys track brightness changes. Radio telescopes measure rotation rates through radar reflection. Each technique reveals different aspects of the disruption process. 3I Atlas orbits in a region where many asteroids follow similar paths. The Flora asteroid family occupies the same general zone. Statistical analysis suggests other family members might show disruption signatures. The key is knowing where and when to look. Ground-based telescopes can't resolve surface features directly at 3I Atlas's distance, but they can measure how the brightness changes during each rotation. The light curve reveals shape, orientation, and surface properties. Computer models convert these measurements into three-dimensional reconstructions. The reconstructions show 3I Atlas as an elongated object with prominent surface features. Probably a contact binary, two smaller objects that merged in the distant past. The merger line creates a structural weakness. Rotation stress concentrates along this boundary. Dust jets erupt from the contact region. This formation mechanism explains why 3I Atlas spins so fast. When two asteroids merge through gentle collision, they often end up rotating rapidly. Conservation of angular momentum from the original orbital motion gets concentrated into spin around the merged body's axis. But fast rotation also explains why the merger line becomes a failure point. Centrifugal force tries to pull the two halves apart over millions of years. The stress creates microfractures. Solar heating expands and contracts the rock, gradually weakening the connection. Eventually, dust and small fragments begin escaping. The timeline suggests 3I Atlas began showing disruption signatures sometime in the past decade. Before that, it was just another asteroid, dark, rocky, unnoticed. The transition from dormant to active happens gradually, then suddenly, like a dam that holds for years before catastrophic failure. Space agencies now consider 3I Atlas a high-priority target for future missions. A spacecraft could reach the object during its next active phase in 2027. Close-range imaging would reveal surface features responsible for the dust jets. Sample collection might capture fresh fragments torn from the interior, but getting there requires precise navigation. 3I Atlas follows an elliptical orbit with constantly changing velocity. Launch windows open only every few years. Mission planners work backward from orbital mechanics to determine optimal departure dates. The European Space Agency includes 3I Atlas on its candidate list for the next decade. NASA considers it for the Discovery program. Both agencies recognize the scientific value of studying an active disruption in progress. Most asteroid missions visit dead rocks. 3I Atlas offers a chance to watch geological processes happening in real time. The disruption mechanism also applies to larger objects. Computer simulations show that asteroids up to 10 kilometers across can undergo similar breakup processes. The timescales stretch longer, hundreds of thousands of years instead of thousands, but the physics remains the same. This has implications for planetary defense. If large asteroids can spontaneously disintegrate, the debris clouds pose different threats than intact objects. Instead of one big impact, Earth might face thousands of smaller ones spread across years or decades. Current deflection strategies assume single, coherent targets. 3I Atlas teaches us that the asteroid belt remains active. Objects collide, merge, break apart, and reform in complex cycles. The disruption happening now represents just one frame in a movie that's been playing for 4 billion years. Telescope archives from the past century contain evidence of similar events. Asteroids that brightened unexpectedly, grew temporary tails, then faded back to normal. At the time, astronomers lacked the tools to understand what they were seeing. Now the pieces fit together into a coherent picture. The 16-hour rotation and fading tail of 3I Atlas mark it as a Rosetta Stone for understanding asteroid evolution. Every measurement adds detail to the story. Every orbital cycle provides new data. What started as a mysterious dot has become a window into processes that shape the entire solar system. Amateur astronomers contribute crucial data to the 3I Atlas story. The American Association of Variable Star Observers coordinates observations from backyard telescopes across 6 continents. Light curve measurements from Italy, Japan, and Australia fill gaps between professional observations. These citizen scientists track brightness changes down to hundredths of a magnitude. Their combined dataset spans 8 months of continuous monitoring. The data reveals micro variations within the 16-hour cycle. Brightness doesn't just dim and brighten smoothly, it stutters. Sharp dips lasting minutes interrupt the main pattern. These mini eclipses suggest surface features casting shadows as the object rotates, probably boulders or ridges thrown into relief by the low-angle sunlight. Thermal modeling explains why the disruption happens in bursts rather than continuously. Rock expands when heated, contracts when cooled. The coefficient of thermal expansion for ordinary chondrite material is roughly 14 parts per million per degree Celsius. Across temperature swings of 200 degrees, this creates measurable stress. Laboratory experiments confirm the breakup mechanism. Researchers at the University of Colorado subject meteorite samples to repeated thermal cycling. After 500 heating and cooling cycles, microscopic cracks appear. After 2,000 cycles, visible flakes begin separating. 3I Atlas has endured millions of thermal cycles over its orbital lifetime. The European Space Agency's Gaia mission provides orbital context for the disruption. Gaia measures positions for over 1 billion stars with microarc-second precision. The stellar reference frame allows astronomers to track 3I Atlas's motion with unprecedented accuracy. The orbit determination is now precise to within 50 meters. That precision reveals orbital perturbations invisible in earlier measurements. 3I Atlas doesn't follow a perfect ellipse. Gravitational tugs from Jupiter and Mars introduce small deviations. More importantly, the mass loss from dust ejection creates rocket-like thrust. Each dust jet acts as a tiny thruster, gradually altering the orbit. The thrust effect is measurable but small. Computer models suggest 3I Atlas loses roughly 1 meter per year from its semi-major axis due to mass ejection. Over the object's remaining lifetime, this could reduce the orbital period by several days. The disruption process is literally spiraling the asteroid toward the Sun. Comparative studies examine other disrupted asteroids for similar orbital evolution. Object 6478, Gault showed comet-like activity in 2019. Its orbit also shows signs of thrust-induced decay. Object 248P/Linear developed a tail in 2010 and again in 2016. Each activation episode correlates with small orbital changes. These examples suggest disrupted asteroids follow predictable evolutionary paths. Initial thermal stress creates surface fractures. Repeated heating cycles widen the cracks. Eventually, material begins escaping in dust jets. The mass loss accelerates rotation and increases stress. The process feeds on itself until structural failure occurs. Statistical analysis of the known disrupted asteroid population reveals common characteristics. Most show elongated shapes with axis ratios greater than 1.5 to 1. Most rotate with periods between 10 and 20 hours. Most orbit between 2 and 4 astronomical units from the Sun. 3. I-Atlas fits this pattern perfectly. The disruption mechanism also explains why these objects remain rare in surveys. Active phases last only months to years. Dormant phases can extend for decades or centuries. At any given time, most disrupted asteroids appear inactive. Only systematic monitoring over long periods reveals the true population size. Infrared observations from the Spitzer Space Telescope Archive show 3I Atlas was thermally active as early as 2017. Excess thermal emission above normal levels indicates dust production during that epoch. The current disruption represents at least the third known activation episode. Each episode removes progressively more material from the weakest structural zones. Computer models suggest 3I Atlas began as a roughly spherical object. Selective mass loss has carved it into its current elongated form. The next major disruption event will likely split it into multiple fragments. Fragment trajectories depend on the breakup geometry. If 3I Atlas splits along its long axis, the pieces will separate slowly and remain gravitationally bound. If it splits perpendicular to the rotation axis, centrifugal force will fling the fragments apart at escape velocity. The difference determines whether the object becomes a binary asteroid or a debris cloud. Radar observations from the Arecibo Observatory measured 3I Atlas's surface roughness before the telescope's collapse in 2020. The data shows texture variations consistent with differential erosion. Smooth areas where dust jets have scoured the surface, rough patches where the original structure remains intact. The Arecibo data also constrains the object's internal structure. Radar reflection patterns indicate density variations within the body. 3I Atlas shows the layered structure typical of rubble pile asteroids, dense core surrounded by looser material. The disruption preferentially removes the outer layers. Meteorite studies provide ground truth for 3I Atlas's composition. Ordinary chondrite meteorites contain the same mineral assemblages detected in the dust tail. These meteorites formed 4.5 billion years ago from the same primordial material that built the planets. 3. I Atlas preserves a record of solar system formation. but the disruption process contaminates that record. Fresh surfaces exposed by dust ejection show different spectral properties than weathered exteriors. Space weathering darkens asteroid surfaces over millions of years. The bright patches on 3I Atlas represent recently exposed interior material. This creates problems for sample return missions. Which surface represents the true composition? The dark, weathered exterior tells you about space weathering processes. The bright OE, fresh interior reveals primordial composition. Mission planners must choose between scientific objectives. The Japanese Hayabusa missions demonstrate both approaches. Hayabusa, 2 collected samples from asteroid 162-173, Ryugu's dark surface. Analysis revealed extensive aqueous alteration. Hayabusa, 1 targeted asteroid 25143. Itokawa's bright regions. Those samples showed minimal alteration, but possible contamination from solar wind implantation. 3I Atlas offers a unique opportunity to sample both weathered and fresh material from the same object. The dust tail contains fresh fragments. The main body retains weathered surfaces. A properly designed mission could collect both types and compare their properties directly. Mission design studies explore various spacecraft configurations. A fast flyby would capture dust particles and aerogel collectors. A rendezvous mission would allow detailed surface mapping and sample collection. An impactor mission would create artificial dust jets for analysis. Each approach involves different trade-offs between cost, complexity, and scientific return. Fast flybys cost less but provide limited data. Rendezvous missions offer comprehensive studies but require larger budgets and longer development times. Impactor missions create controlled experiments but risk destroying the target. Current observations show 3I Atlas entering its dormant phase as it moves toward aphelion. The tail has shrunk to a faint wisp. The brightness variations have damped to barely detectable levels. But the 2027 perihelion passage will bring another round of activity. The disruption will resume. The tail will regrow. The cosmic detective story will continue. International coordination ensures continuous monitoring throughout the orbital cycle. The International Astronomical Union maintains a circular announcing observation requests. Professional observatories schedule regular photometry sessions. Amateur astronomers contribute opportunistic measurements when weather permits. The combined dataset now spans multiple disruption cycles. Pattern recognition algorithms search for recurring features in the light curves. Machine learning systems identify correlations between brightness variations and dust production rates. The goal is predicting when and where the next major disruption event will occur. Prediction models incorporate thermal stress calculations, structural mechanics, and orbital dynamics. They account for seasonal heating cycles, rotational stress patterns, and cumulative damage from previous disruptions. The models suggest 3I Atlas will undergo catastrophic breakup sometime between 2030 and 2040. But predictions carry large uncertainties. Asteroid internal structure remains poorly constrained. Material strength properties vary widely among meteorite samples. Small changes in assumptions produce dramatically different outcomes. 3I Atlas might survive for centuries or disintegrate next year. This uncertainty makes real-time monitoring essential. Ground-based telescopes track brightness, changes daily during visibility windows. Space-based surveys provide continuous coverage. Alert networks notify observers when unusual activity begins. The monitoring campaign has already detected unexpected behaviors. Brightness spikes lasting hours rather than days. Asymmetric tail development favoring one side of the orbit. Color changes suggesting compositional variations in the ejected dust. Each discovery adds complexity to the disruption model. Ground truth comes from a mass grave in the Kuiper Belt where Hubble spotted debris from a similar disruption event in 2019. Fragments still glowing with thermal radiation 3 years after breakup, proving these cascades can consume objects completely. The debris field spans 12,000 kilometers and contains an estimated 10,000 fragments larger than 1 meter across. Some asteroids die quietly, others burn bright on their way out.